Synthetic division. These are notes and practice problems to learn how to use synthetic division with polynomials. First of all, we have to make sure that our polynomials are all in descending order. And I'm going to go ahead and add in a little s here to make this plural. Polynomials plural must be in descending order. And that includes the dividend and the divisor. Okay, if a power of x is missing, use 0 as a placeholder, exactly like we did with long division. For synthetic division, we list the coefficients only. But we're only able to use synthetic division if the divisor is linear. Okay, the divisor has to be linear. In other words, the divisor cannot have a power higher than 1, a power of x that's higher than 1. It's not possible to do with synthetic division. So if you have one like that, you have to revert back to long division in order to divide. The 0 or the root is used as the divisor. So if given a factor, we have to convert that into the 0 or the root. And just as a reminder, a 0 has other terms that mean the same thing. A 0 could also be referred to as a root or a solution or an x-intercept. Any of those words describe the same thing. So they might be used interchangeably throughout the lesson or through your directions or practices, whatever you may have. 0, root, solution, or x-intercept. So in order to start the process and divide synthetically, the first thing I do is I bring down the first coefficient in the process. So that would be here. Bring down the first coefficient, and then you begin a repeated cycle of multiplying and dividing. Excuse me, not multiplying and dividing, multiplying and adding. Multiplying and adding. Okay, so let's take a look at an example. Here's our first example here. This is my dividend. Here is my divisor. The divisor is written in a factored form, written as a factor. If the factor is x plus 3, then that means the root is negative 3. The root is negative 3. So from here, I set up a little box system here. Basically, you'll start out by listing the root, and then you will list the coefficients in your dividend. So that's where these things are coming from. 2, negative 5, negative 1, and 3. I check to make sure I have everything in descending order. So x to the third squared, x to the first power, and then my constant. and I don't have any powers of x or a constant missing. There's no missing terms. So now I can begin the process by bringing down the first coefficient. You have to bring that down first and then begin. I multiply, I take the -3 and I multiply it by the 2 here. -3 times 2 is -6. And I'm going to put the answer, I'm going to put the -6 in this position. And then I'm going to add straight down that column. -5 plus -6 will give me -11. And then go again. -3, we're going to multiply -3 times -11. -3 times -11 is positive 33, and I'm going to put that answer here. And now I'm going to add straight down in the column. That gives me 32. And go again, the whole process all over again. We're going to take the -3, we're going to multiply it by 32. 32 times 3. I'm going to put the answer in this position here. And then I'm going to add straight down in the column to get, oh, I'm sorry, this is a negative. So 32 times -3 is -96. Add straight down the column. I get -93. And then I'm finished with the division process. From here, I need to take these coefficients and write them into the quotient. A couple things to make notice of. Whatever degree your dividend is, notice that the dividend that we have is a degree of 3. Its highest power is 3. Your quotient is always going to be 1 less than that. So if I have a degree of 3 in my dividend polynomial, then my quotient is going to be a degree of 2. So the highest power of x I'll have in my answer will always be 22. And that's true for any kind of division that we do with polynomials, long or synthetic. And so the way that I like to write my quotient is by first remembering that the far right coefficient that we have is actually the remainder. This first number is going to be my remainder. This second number here is always going to be the constant. In other words, it does not have a variable with it. And then I start with my lowest power of the variable. So this would be x to the 1 power, and then x to the 2 power, x squared, so on and so forth. The more coefficients I have, I just continue to add 1 to the power of the variable as I move to the left. So that kind of sets me up to be able to now write my quotient, 2x squared minus 11x plus 32. And then with the remainder, we write this, we tack it on at the end as a fraction with the remainder in the numerator and the divisor, the entire factored divisor in the denominator. So x plus 3 belongs in the denominator there. Okay, and there we have our final answer. So we're going to neatly put a box around that. And there we go. Okay, so let's go ahead with example number 2 now, and I'd like for you to try to set it up. See if you can set it up by listing the coefficients and writing your divisor in the correct spot. So I'm going to wait just a moment or two, or you can pause the video, set it up, and then check with what I have. Okay, so my dividend was missing a power of x. I'm missing an x squared term. So I basically have to put in a placeholder. I have to put in a 0x squared in order to account for that position in my division problem. List the coefficients, including that 0 there. The divisor is the root or the 0, so it's always going to be the opposite of this sign here. Technically, what we're doing is we're taking this factor x plus 3 and setting it equal to 0. So by doing that, if I take the factor and set it equal to 0 and then solve for x, that's how I come up with the 0. It's always going to be the opposite sign of that number inside the binomial there if it's listed as a factor. So back to my synthetic division, bring down the first coefficient, and then start your multiplication process and then add. -3 times 1 is -3. Now I'm going to add straight down and multiply. -3 times -3 is +9. Add straight down. Multiply. Add straight down. Okay, we're finished with that. The very last value is always my remainder. So now I'm ready to write my quotient. This is the remainder. This is the constant. Then I have x to the first power, x to the second power. So my quotient is x squared minus 3x minus 10. There's no remainder here, so I'm all done. Okay. Much cleaner of a process than long division is, but again, both types of division are useful. There's a statement here on the page that says synthetic division can also be considered a method of factoring. In the previous example, we had our dividend here, x to the third minus 19x minus 30. It was divided by this factor x plus 3, and my answer was x squared minus 3x minus 10. So what that really means is if I were to multiply my divisor, multiply the divisor times my quotient, then I would end up with the dividend. So the inverse process is a check, in other words, or this is basically what division does. It shows up in ways that we can see a factor multiplied by the dividend, a factor multiplied by the quotient will equal the dividend. Ultimately, everything has to work back together in kind of checks and balances. So knowing this now, we are brought to an important theorem called the factor theorem, which ultimately just states and has been proven that if a polynomial is divided by something and we get 0 for the remainder, then what we divided by, that is actually a factor of the polynomial. Okay, if I do the division and I get a remainder that's other than 0, so any other number besides 0, if I have a remainder at all, then I do not have a factor. So being able to use synthetic division to show whether or not the remainder is 0 or if it's something else is a way of factoring. It's a way of showing whether or not I have found a factor of that polynomial. So here's an example on my next page where I can use synthetic division and then I can state whether or not x minus 1 is actually a factor of this polynomial here. So let's go ahead and set up our synthetic division. X minus 1 is the factor. That means the root would have to be positive 1. List my coefficients. Make sure I have all powers of x accounted for. Nothing's missing. Draw a line, bring down the first coefficient, and now start to multiply and add. 1 times 1 is 1. Add. 1 times negative 2. And add. 1 times negative 3. And add. Okay, the last value I get is always my remainder, and then it's my constant, and then I begin with x to the first and x squared. My quotient is going to be x squared minus 2x minus 3. I've ended up with a 0 remainder. So I now have shown that x minus 1 is indeed a factor of that dividend. So we can make a statement that says x minus 1 is a factor of this polynomial based on the factor theorem. Okay, you do the next one, pause the video, and you do this next one by yourself, and then check to see if you have the right answer. Oops, mistakes. Okay, let's go ahead forward to the next page and then discuss one more thing. This is called the remainder theorem. This says that I have found a factor if I evaluate the polynomial at the root or at the zero and it equals 0. If that happens, then I know this is another way. If this that I know that I have a factor. So, in other words, if we're given a polynomial, and notice this is written as a function here, p of x is equal to this polynomial. If we want to show that x plus 3 is a factor of that polynomial, then I can do this. I can evaluate p of negative 3 because evaluating at the root, negative 3 is the root or the 0. And that would mean that x plus 3 here, the divisor, would be the factor. So opposite sign, or consider setting that x plus 3 equal to 0 and solve. That gives me the root. So if I can evaluate my function, evaluate the function at negative 3, that means take this function and in place of x, we're going to put negative 3 and we're going to calculate. We're going to find the value, find the number. So p of negative 3 means everywhere I see x, I'm going to substitute in a negative 3, and then I'm going to calculate. Okay, so from here, we have to be very careful, go slowly, be careful with your signs, and make sure that you're following order of operations. So we cube the negative 3 and get negative 27. Square negative 3 and get positive 9. And then let's go back through and multiply 6 times 9. And now we need to combine our like terms. So negative 27 plus 54. Positive 27 minus 15. I end up with 0. I end up with 0. So I evaluated this polynomial at negative 3. My solution was 0. So what this means is that it's basically like doing synthetic division and getting a 0 remainder. Whatever you get when you evaluate, so like this value here is the same as the remainder of the division that I would get. So since this is 0, our statement would be, based on the remainder theorem, that x plus 3 is in fact a factor. Okay, so evaluating the polynomial at the root is like doing the division and seeing what the remainder is. It's like a quickie glimpse of what is the remainder. If you don't care about the rest of the division at all you really care about is the remainder. Do I have a remainder? Do I not? Is it 0 or is it something else? That's really the only information that I need to know in order to be able to decide, is this a factor or is this not? So since I've evaluated at the root, I got 0 as the remainder. Therefore, I can go ahead and make the statement that, yes, x plus 3 is a factor. Okay, pause the video, and now you do the next one on your own. Okay, so we end up finding that the remainder is negative 17. And so this means, therefore, negative 3 is not a root of f of x. No, negative 3 is not a root of negative x. And if we were asked, how do I know that? Or, what makes you say that? Give us some support, give evidence. Then it would be based on the remainder theorem. Okay, one more thing that we are able to do, and that is I can start out with a degree 3 or 4 polynomial and having a possible factor. Start out using synthetic division, confirm that I do indeed actually have a factor, and then with the quotient, with what's left over, since it's small enough to use my factoring skills, I can then factor in order to find the other factors or find the other roots for that particular polynomial. So given any linear factor, I'm told to find all of the zeros. So what we want to do here is, first of all, you want to use synthetic division. You should always end up with no remainder. If you get a remainder, then you have to stop, but you should end up getting no remainder. Then you want to use the quotient and you're going to factor it. So that's going to give us the remaining factors, and we can also make a list of the roots as well. So let's get started by setting up synthetic division. X minus 2 is the factor, so I'm going to use synthetic division. I'll need the root. The root is positive 2. Now I'm going to list my coefficients, making sure that I have every power of x accounted for and that they're in descending order. Draw a line, bring down the first coefficient, multiply, and add. Multiply and add. Multiply, add, and I should end up with 0 remainder. Okay, write out your quotient. And now we want to factor this. Factor this. So however you like to factor, whether it's box method, grouping, whatever you want to do, you need to factor. Okay, so here are my other two factors. I had one that I was given in the beginning. I found two more, and now I'm able to go to my final answer and make a list. I'm supposed to list all, it says to find all the zeros. So first I'm going to list all the factors just because I want to, not because I'm required to, but the factors, the first one I was given, and then these two I found. And so ultimately I can multiply those three factors together and I should end up with the original polynomial from the very beginning of my problem. When I multiply all those factors together, that should be my answer. So it is possible to check. Once I list all the factors, then I can list all the zeros or all the roots. And so the first one is positive 2. This one is negative 1/2, and then positive 4. So in case you're curious, the process for finding the zeros is what we do here. The basic algebra that's happening in between this step and this step is we set each individual factor, we set equal to 0 and then solve. So it's easy to see if there's no coefficient of x, but if I do have a coefficient of x, like for this one, you might need a little bit of practice in order to get what we end up with. Just itty bitty little algebra 1 type fractions. So that's where I came up with 1/2. So this process here is we set each individual factor equal to 0 and then solve in order to get the zeros. Okay, lots and lots of practice to be done on pages going all the way through. Let's see. All the way through 13. So you should be able to complete all notes and practice problems in the packet from page 1 through page 13. And answer key is posted on Canvas.